All right, so I had a question about ammonium cyanide. Ammonium is a +1, cyanide is a -1, so it should look like something like this. But, for one, ammonium is a soluble salt. And soluble salts are strong electrolytes. Strong electrolyte means it's just going to ionize into ammonium ions and cyanide ions. Now, ammonium itself is what we call a weak acid, and cyanide is a weak base. And so ammonium cyanide has an acid and a base in the same compound. And so both of these are weak. Weak means they partially hydrolyze water. So ammonium will hydrolyze water like this to form ammonia plus hydronium. And so we look at the Ka for this. The Ka is like 5.6 times 10 to the minus 10, like that. Cyanide here is also going to hydrolyze water. This is going to make HCN and hydroxide. And this is going to have a Kb. The Kb value for this is equal to Kw over the Ka for HCN, the conjugate. And so Kw was 1.0 times 10 to the minus 14. And Ka for HCN is, we used it the other day. Was it 6 times 10 to the minus 10? Does somebody have their notes from last time, I think? Five times 10 to the negative 10? 6? 6 times 10 to the negative 10. Thanks. I think it was 6.0. So that gives it a Kb value of 1 times 10 to the minus 14 divided by 6 times 10 to the minus 10. .66 10 to the negative 5. Oh, let's compare which one's bigger, 1.66 times 10 to the negative 5 or 5.6 times 10 to the negative 10? Yeah, 1.6 times 10 to the negative 5. So ammonium cyanide is going to be basic. Should be an overall basic solution.
So will it always come down to whichever value is larger in that situation?
When you have a situation where there's both an acid and a base, which one's larger? Now the problem is both of these are weak. Overall, it's a basic solution. To solve this, we do simultaneous equilibria. With the Ka for ammonium, the Kb for cyanide, and Kw for water. We have to do KW. KW is for all these because KW is going to contribute hydronium and hydroxide to solution. Did I post the methods used to solve simultaneous on Canvas? Did I forget to post that? Actually, maybe I forgot to record. I'm recording that. Yeah. I forgot to post it. I'll post it this week. Was that the question there for ammonium cyanide?
Yeah, that answered the question.
Okay, just want to make sure. All right, any other questions? Ammonium cyanide's tough because it's simultaneous. If we only had a weak acid or weak base, so let's say there's only ammonium, like say ammonium chloride, chlorides ignore, nitrate ignore, then it's a lot easier. Or if we only had cyanide, like sodium cyanide, you know. But when we have ammonium and cyanide, that becomes a really difficult problem to solve. Quantitatively. We could solve it qualitatively, just compare the two. So. All right. If there are no questions, we're going to talk about the lab today. Today we're doing the pH titration.
Question on the previous lab reports.
Mm-hmm.
Did you say you were going to go over how you wanted us to submit those?
Yeah. We're almost done through chapter 17. So what we're going to do is we're going to calculate the Kas and the Kbs for the solutions that we did from experimental data, and then you're going to compare it with the accepted Ka and Kb values out of the book, Appendix D, and then determine the percent error, and then that's it. When we use the pH meters, that lab. The lab report for the pH experiment that we did last week, or it was the week before, I'll talk about. I want you to do calculations for that, but I'll do the calculations once we're done with chapter 17.
I mean, we haven't done.
We haven't finished it.
Wait, no, we did. We did turn in the first lab because you were like, you wanted to see the data and it would be done. I guess I was thinking the second lab or the third lab. So what you were talking about with the data was for the second lab, right?
The data was you use the pH meter to probe it. That one we're still going to do, but I just want to get through the calculations here on chapter 17. Then you'll do the calculations for that.
And then the third lab was the salt one, I believe.
Yeah. But I'm going to be doing that one.
Third lab was the salt one. Are you talking about?
Building complex.
Oh, the synthesis one? Yeah, once we get the crystals for that, then we'll start. You know, we got to weigh the crystals out. So you're going to do a progress check on your crystals today. Make sure they're growing. If they're not growing, then you got to take some interventive action. Okay. And then the crystal, the one that you're trying to grow crystals on, that one is going to be a formal scientific report.
So is that going to be the turn in?
Yeah, you're going to turn that in, but later. Once we get the crystals, then you'll have some time. We need to get the crystals, clean them, weigh them. That way we can calculate our percent yield, and also we can see how our product turned out. This pH titration will also be a formal scientific report. So today's experiment will be too. You have extra time for formal scientific reports. I'm not sure which one we'll do first because it depends on how big your crystals are. If the crystals are practically done. Maybe we'll do that one first, but we'll have our data for this one coming up, and then the discussion is in chapter 18, so we'll see. We'll probably do the crystals first. Okay, any other questions? When we're doing a pH titration, you're going to have to check out the equipment. And not only are we going to get the pH meter, but we're also going to get the burette and whatever else. And so with the pH meter, do you remember about the calibration? Okay, the buffer solutions are back there. And what we're going to do is we're going to reuse the buffer solution. Buffer solution is kind of expensive, so it's not like a disposable one-time use. Buffers are meant to be used multiple times. And so it's okay if there's a little bit of dilution or contamination of those. They should maintain that stable pH. The job of the buffer is to maintain a stable pH so that we can use that for calibration of our instruments. Okay, so the pH titration, you're going to run an unknown solid organic acid. You know, most of the acids that you've dealt with are gases, like hydrogen chloride gas, which makes hydrochloric acid, or liquids like acetic acid is a liquid, but these are solids. These are large carboxylic acids, and so they're solid at room temperature. And what we want to do is we're not going to do a normal titration. Normal titration, we're only interested in one point, the end point. But what we're going to do is we're going to monitor pH with milliliters of sodium hydroxide titrant. And the pH that we're going to observe is going to look something like this, where it starts off low and then goes up a little bit and then kind of flattens out, and then has a very steep rise here, and then plateaus and then flattens out. So we're going to do this all the way out to 50 milliliters, or roughly 50 milliliters, you know, the full contents of the burette. But normally in like Chem 1A, you'd stop here. You'd stop at a point called the end point. The end point is where the indicator changes color. And so phenolphthalein, which we're using for our titration, is going to change color here. It's going to go from colorless to pink. But it turns out that that's not what we call the equivalence point. The equivalence point is this point of inflection here. This is the equivalence point. The equivalence point is when we hit the right stoichiometric ratio. And so in your titrations, like in Chem 4 and Chem 1A, where you use phenolphthalein, you actually went past the stoichiometric equivalence point. That's because the indicator didn't change color until just slightly after. But the error is very small. Not only is the error very small, it's a systematic error. We should be able to calibrate that out.
What does the thing on the left say? Yeah, that.
This one?
Yeah.
Phenolphthalein.
Okay.
It's so long I didn't want to spell it out, but I'll spell it out. Phenolphthalein indicator changes color. So we go from colorless to pink. There. The error that's associated is very small, like less than a drop usually. Yeah. You hit the equivalence point, then less than a drop, you're already there. So it's negligible error kind of thing, and then it's systematically removed. So do you see, we're going to hit this kind of wave here. But what we want to do is we want to pinpoint exactly, what the wave looks like and where it starts and where it ends and how big it is, this kind of thing. Equivalence point is when you have just the right amount of acid and base, but the problem is we're just using these organic dyes, and the organic dyes aren't designed for titration. They're, they just happen to be close enough. And so phenolphthalein, even though we hit the end point there, we've actually passed the equivalence point. We actually passed the stoichiometric equivalence point. And so we have to have a little bit of excess sodium hydroxide, and then it stops. In a true titration, we want to hit the equivalence point. In this titration, we'll be able to pinpoint the equivalence point easily.
So how come you said that we're going to get to an endpoint using phenolphthalein, but it's not going to be the equivalent point because it happened before?
It depends on what the titration is. So if we do HCl sodium hydroxide, hydrochloric acid and sodium hydroxide produce sodium chloride and water. So does phenolphthalein change color at pH 7? Sodium chloride is pH 7. It's supposed to be pH 7. Does phenolphthalein change color at pH 7? No. Phenolphthalein changes color at pH 9. If phenolphthalein changes color at pH 9, then we've already passed it, because at the equivalence point we should be at pH 7. But to go to pH 9, we have to add extra base to get to pH 9. So here, at pH 7, we should have been done, but phenolphthalein is still colorless. We have to bump it up to pH 9. Well, pH 7 to pH 9, that's a huge error in pH, right? It's a huge error in pH. However, it's a tiny error in milliliters of sodium hydroxide. It's a tiny error in milliliters of sodium hydroxide because this is almost like a vertical wall. And so a tiny error here means a huge error here. But we don't care about that. We just care about the error in the X, not the error in the Y. Does that? And so we use phenolphthalein, even though phenolphthalein changes color at pH 9, not pH 7. But if we do a weak acid, the equivalence point is like pH 8. So pH 8, pH 9 is a small difference, in terms of milliliters here. Big difference in terms of pH, right? We could use any indicator. We could use like methyl red or methyl orange. It changes color down here. But the same thing, we would have been before. There's one that's close to perfect. The one that's close to perfect is bromethymol blue. I think bromethymol blue goes from yellow to green to what is it? Blue. Yeah. And so yellow. So at pH 7 it changes colors, but when you talk to people, they say, "Oh, that looks green," and other people will say that looks blue. And so it's hard. Even though it's perfect, it's hard for people to judge the shade of green that's pH 7, because it gradually changes from a lighter shade of green to a darker shade of green. So it's not easy. So people prefer phenolphthalein because it just goes from colorless to pink. Most people can see the color change, rather than a subtle yellow to green to blue transition. And so using phenolphthalein is a little bit in error, but it's okay. The error is small in milliliters of titrant, and so we're all right. Now, we're going to be monitoring this continuously, but the problem is that let's say you add a drop of sodium hydroxide. Does it mix instantaneously? No, it takes time to mix. So you got to stir it and mix it until you get a stable pH reading. So each time you add some sodium hydroxide, it takes like a minute or a few minutes to equilibrate, and then we can move on. So let's say it takes 1 minute. Add a drop, let it stir, wait 1 minute, and then record it. Okay, if we were to do it drop by drop, let's say drop by drop would be perfect because that would be the highest resolution we could get, 1 drop resolution. Actually, no, it's not the highest. Do you know how to do a half a drop? Have you ever heard of a half a drop? Some people might say a half a drop is impossible because a half a drop won't fall down off the burette. Well, you don't let it fall, you force it down. How can you force a half a drop down?
You like, I don't know, take one of those scoopers, dip it in there, and like wait for it to drop off.
Yeah, or just use a squirt bottle and wash it in. But we can't do it here because if you add a squirt bottle and wash it in, what happens to the concentration? If you add water, you're doing what we call solution dilution. If you do solution dilution, the pH rises. You know, if you keep adding more and more water, what's going to happen to the pH? The pH is going to converge at pH what? Any solution. It could be strong acid or strong base. All of them at infinite dilution are going to converge at pH 7. It's going to be like pure water. And so we don't want to do that because if we have an acid here and we just dump water, more water, the pH is just going to rise. We don't want that to happen. And so the highest resolution we can get for this titration is 1 drop. You know, we could add a drop, wait, because we don't want to add water or anything like that. But do you know about how many drops are in a milliliter? This is kind of not very practical. You actually did this experiment if you took Chem 1A or Chem 4 here because we do, how many milliliters is 1 drop? That's not a very useful number to remember, how many milliliters is 1 drop. What's a much more useful number to remember is how many milliliters are in a drop. So I want to change the report sheet. Rather than you calculating the volume of 1 drop of water, you know, you add like 20 to 60 drops and then you measure the volume. Rather than calculating the volume of 1 drop of water, it'd be much better to calculate how many drops are in 1 milliliter. And you do that, it comes out to about 0.05 milliliters per drop, or if you do my calculation, it comes out to about 20 drops per milliliter. So if we have 20 drops per milliliter and we have 50 milliliters in the burette, that's 1,000 drops. And if each drop takes about a minute to record the pH, that's 1,000 minutes. Do we have 1,000 minutes in lab? No, we don't have 1,000. So we have to make some compromise. And so what would be nice is to map this at the highest possible resolution all the way through here. But we don't have time. And so what we're going to do is, where we think it's going to be fairly flat, and we can look at the pH, we're going to collect data at larger intervals. So here, we'll collect data right at the beginning, and then we'll go 1 milliliter interval. So this would be 1 milliliter, this would be 0 milliliter. And we'll collect 1 milliliter intervals as long as the pH doesn't change much. And you should see the pH stay flat initially. But right when you see it starting to increase, we got to slow down. Because if you collect 1 milliliter intervals here, you've missed it entirely, and you can't pinpoint where it rose. And so we need to go drop by drop. Probably before this, we should start slowing down and go drop by drop so that we get a lot of data in here. And it's so steep, this steep rise is probably only going to be defined by maybe 2, 3, 4 data points at the most. You know, I have more here, but it's not really going to be that well resolved. And so, in other words, we are going to go wide and then slow down. We're going to slow down here until it plateaus, and we notice it plateaus. So we're going slow here, and we're going to collect data at tight intervals. And then once we see it plateaus and not much changes, then we're going to go back to wide intervals, out to 50 milliliters or close to it.
Do you have like an approximation about when we would expect the drop, like the big jump?
Yeah, do I have an approximation when we expect this wave to occur?
Yeah, like maybe in 20 milliliters.
Actually, I have no idea. I have no idea. So 2 choices. One, you keep an eye on the pH and start to see it rise. When you start to see it rise, slow down, right? It'll stay flat and then start to rise a little bit and then start slowing down. Or 2, what we do is we do something called a trial titration first. And this will be a sacrificial titration.
Yeah, where we see the big jump. And then we can
Yeah. And we're not going to look for the jump. In our sacrificial titration, we're not going to use the pH meter because the pH meter takes too much time. Instead, what we're going to use is phenolphthalein. And so we know that this big jump here should occur when phenolphthalein changes color, plus or minus a little bit, right? And so what we're going to do is we're going to run a trial titration to see approximately where phenolphthalein changes color. And then we're going to optimize the amount. And so let's talk about this. So first, we're going to do a trial titration. So you're going to get a sample of point XXXX grams. Anywhere from like 0.1 to 0.3 grams. In that range should be fine. Don't go too high. Try to keep it close to 0.1 because it depends on your acid. But our target, in case you overshoot it, don't worry. If you overshoot it, we're going to go with it. And then you're going to run a normal titration. A normal titration is in an Erlenmeyer flask. We always do titrations in Erlenmeyer. And then we're going to have our sodium hydroxide standard solution. Our sodium hydroxide standard solution is going to be 0.1107 molar. And then we're going to titrate this to the end point and stop. The end point is going to be like this. It's going to be colorless. And then we're going to add, in this case, we could add a half a drop, because we're not measuring the pH. And adding water is not going to change how much acid we have in there. And so we could actually go half a drop here, or a drop. And so 0.5 to 1 drop, we want to go from colorless to pink. How long does the pink color have to persist? For, 30 seconds, yeah. 20 to 30 seconds with swirling. It could disappear after this because there's CO2 in air. It's going to neutralize it. So it just has to persist for 20 to 30 seconds with swirling. And then we're done. All right. So what I'm going to do is I'm going to figure out how much. So over here I'm going to add y milliliters. And down here I'm going to put in, let's say, 0.1 xxx grams. So I have 0.1 xxx grams. We want to be as precise as possible because this is quantitative. Over y milliliters. And then this is going to give us z grams over, our target is 30 milliliters. We want this, to be where the wave occurs, the big wave. And so we're targeting 30. I would target 35 myself, but the instructions say 30. So we're going to target this to be 30. So to answer your question, 30 milliliters.
Okay.
And the way we're going to get it to 30 milliliters is by calculating how many grams we need so that it hits it at 30 milliliters. But even though our target's 30, we're going to slow it down before 30. Like 29, maybe 29.5. It depends on how well your titration went. Now, the titration could go very well or not so well. So let me talk about relative error here. Let's say you had a 1-drop error in 5 milliliters versus a 1-drop error in 40 milliliters. And you might go, this is the same. I just have a 1-drop error. But this is relative. This is called relative error. Yeah, your absolute error was 1 drop. But a 1-drop error, and you only have 5 milliliters, that's 100 drops. So it's a 1-drop error in 100 drops. So that's like a 1% error. It's not terrible. But compared to 1-drop error in 40 milliliters of titrant, in 40 milliliters, that's 800 drops. 1-drop error in 800 drops is not a big deal, right? Small error. And so we have to worry about that. Some people's trial titrations only take like 4 milliliters. If it only takes 4 milliliters, then you got to worry about relative error. And that means when you do that calculation could be off a bit. And so it's happened, like for example, this morning, people started collecting data at 1-drop intervals, and they collected it over a range, around 30 milliliters, and then they stopped. But during that range, it was completely flat. And they stopped and they widened the interval. And when they widened the interval, then it shot up. But the problem is they don't know exactly where it shot up because there's a 1-minute window that's got no data. It's invisible in there. So they don't know if it shot up right at the beginning or if it shot up right at the end. So I was trying to explain it to them. Here. I was trying to explain to them that what we want to know the middle of the wave. The middle of the wave is going to be the equivalence point. So our target is the middle of the wave. But they have a data point here, and then 1 minute later, 1 milliliter later, they have another data point here. So we don't know if it shot up right at the beginning here, right after this, or right at the end here, right before this end point here. And so that leads to a big error in where the equivalence point is. It could be anywhere in this range, because we don't have the data there.
So it's not the time, it's the volume that you're concerned about with that.
Yeah, the volume. The time, we don't care, except we need to finish before the lab is up.
So in the syllabus, it says we have 2 days to do this lab, so like what should we have done today, or
Try to do all of it.
what makes sense?
Try to, so many, since this is a formal report, you have to analyze the data. And
Wait, this titration is also formal?
yeah,
Okay.
this titration is a formal report. And the amount of time that's wasted trying to analyze poor data is large because you don't know, if it's at the beginning or the end, and we have to identify the unknown acid.
I just wrote out a little bit, so I can.
So it's important that we get good data for this. And so we're going to calculate our Z. Z grams is what our target mass should be. And we want it to as many sig figs as possible. So it's going to be Z point Z, 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 Z grams. This is, our balances in here are centigram balances or 100th of a gram balances. Those aren't good enough. So we're not going to use our balances here. We're going to go across the hallway here, and the side entrance to the Chem 1A balance room is open. You're going to weigh the samples there in the Chem 1A balance room. So hopefully your trial titration went well. If your trial titration went well, then this is what we're going to do. Now we already know we need to slow down before 30 milliliters. There's one other issue, and this is, if it's monoprotic, then we're fine. Just slow down before 30 milliliters. But we don't know if it's monoprotic or diprotic. Your unknown might be diprotic. Phenolphthalein catches the second wave of a diprotic. The first wave, it doesn't. Oops. And so what we're going to do is, this is about 30 milliliters here. We're going to cut that in half and go down to 15 milliliters. If it's diprotic, our first wave should occur at 15 milliliters. And so what we need to do is we need to slow down before 15 milliliters and start collecting data at a tight interval. That way we can see the first wave here. The first wave is more gentle than the second wave. And then it's going to flatten out a bit, and we can widen the interval. And then before 30, we need to tighten up the interval. Drop by drop is best. And the second wave is a lot bigger. And then it flattens out, and then we can widen up the interval again. So hopefully what we have is we have enough data to nicely resolve the first wave here, and enough data to nicely resolve the second wave. That is, we can pinpoint exactly where this rise is. So, since you don't know if you have a monoproduct or diproduct, you're going to slow down here. What you might see is this flat line. Or what you might see is that there's a tiny wave. And then, for sure, everybody's going to see this around 30. And so what we're going to do is we're going to take wide intervals to save time where nothing much is happening, where it's kind of flat, here, here, here. And then narrow intervals where we might see something happening.
Could it only be monoproduct or diproduct?
Yeah.
So during the like trial run, we won't be able to tell if it's monoproduct or
No, you can't tell.
So then how many rounds are we doing after that to like get the wave?
No, we're only doing one.
Okay.
Yeah. So we're going to do a trial titration. Trial titration, you can only see phenolphthalein. You can only see the endpoint. You don't see the waves. You don't see the structure at all. You just add until the color changes to pink.
So then after like the trial.
After the trial, then you're going to set up a pH titration.
So how many trials with like the pH?
Only one. Only one trial, but we're going to do two. We're going to do today and Wednesday. We're going to do repeat. Normally I only do one, but last time I taught this, so many people had kind of garbage data. It was a big headache. So they ended up having to throw away their data and use somebody else's data. Well, I don't want that to happen this semester. This semester, everybody should have data they can analyze. Regarding monoprotic or diprotic, a lot of people have diprotic acids, but they don't see the first wave. They don't see the first wave because the more water you add, the higher the pH is. So let's say the wave is down here, but you add so much water that you're already above the crest of the wave, so you don't even see it. And so what I say is what we want to do is we want to dissolve the acid in a minimum of water. We don't want to add more water than necessary, because if we add more water than necessary, then we're unnecessarily diluting it. And the more we dilute it, the higher the pH we start out with. And so our goal in dissolving it in the minimum of water is to start off at the lowest pH so that we can observe the wave. Does that make sense? However, this write-up is written for any acid, and some acids are more soluble, some acids are less soluble. In fact, some acids aren't very soluble at all. Some acids are so hard to dissolve, you need a lot of water to get them to dissolve. And so if they're writing a procedure that they have a one-size-fits-all procedure, it's like, this is an analogy I should have probably used in the morning, but it's like you go to the shoe store. You go to the shoe store and they have one-size-fits-all shoes. Well, if it's one size fits all, how big is the shoe, you know? Maybe they only have size 15 shoe, but if it's, you know, maybe everybody. Do you think it's going to be very effective? No, and the same thing here. One size fits all procedure is the same thing. So in chemistry, we always adjust. I always tweak the procedure. You know, even though the procedure says to do this, I always tweak it because I know what they're trying to do, and they're trying to take the one size fits all approach. So the one size fits all approach says dissolve it in 100 milliliters because they figure 100 milliliters is plenty of water. It should dissolve everything, right? But the problem is that you're going to miss. A lot of people are going to miss the first wave. They aren't going to see the first wave because it's so dilute. I mean, okay, take your acid and dissolve it in a swimming pool. What's going to happen to the pH? The pH is going to go close to. You aren't going to see anything. You know. The more and more you dilute it, the closer and closer you're going to get to 7. In fact, some people had a starting pH of 7 today. This is just way too much water.
So, how much should we?
A minimum of water. A minimum of water. In other words, you know, you add a little bit of water, see if it dissolves. If it doesn't, add a little bit more. Add a little bit more. But what people were doing this morning is they dump in 100 milliliters of water in there. That's not a minimum of water. Or some people were dissolving it in a minimum of water and then afterwards dumping in 100 milliliters of water. But, you know, then it kind of defeats the purpose. So what we want to do is we want to dissolve it in a minimum of water. However, what we have to also recognize is that you have a pH probe. We're going to do this in a beaker so we can fit in everything in here. And the pH probe is going to have a glass bulb here. This glass bulb has to be completely submerged. So let's say you were very successful in dissolving it in a tiny bit of water. Unfortunately, you're going to have to add more water. You need enough water to completely submerge the glass bulb, otherwise you're not going to get a good reading. And so what I say is dissolve it in a minimum, but if it's highly soluble, you might have to add more water.
Can we technically tilt the glass?
No. You can't tilt the beaker because what we're also going to put in here is a magnetic stir bar. The magnetic stir bar is this Teflon coated magnet that looks like a little cigar shaped thing, oval shaped thing. And then it's magnetic, so we're going to put this on a magnetic stirrer. And so we put it on a magnetic stirrer and then just turn up and what you want to do is you want to spin the stir bar so it spins at the maximum RPM without splattering. You don't want any splattering to occur, and splattering is much more likely to occur in a beaker than an Erlenmeyer. That's why people prefer Erlenmeyers for titration, because it's hard to lose solution due to splattering.
Can we use a smaller beaker?
Yeah, use a small beaker, but you have to fit in the stir bar, the pH meter, and then you have to have enough room for the tip of the burette
So what
to go there.
size do you recommend?
I wouldn't go with the probably 100 or 150. You might have to use 150 because of the probe and stir bar are probably going to collide with one another in 100. They have different shapes. We have these long oblong ones, but they have circular ones with little fins on it, which are probably better. You probably could get away with 100. 100 or 150 should be okay. All right, then you're going to take a reading and then add a milliliter, take another reading, add a milliliter, take another reading, and then when you get close, you know, to 15, like before 15, slow down. Try to go drop by drop to see if you could see the first wave. And then before 30, you know, maybe like 29 and a half, slow down. But it depends on how confident you are in your trial titration. If your trial titration went really well, then yes, you can pinpoint it like 29 and a half. If your trial titration has some uncertainty, then maybe start sooner, like 29 milliliters, and then collect later. You know, what you're looking for is a rapid rise in the pH. And this rapid rise in the pH is up to like 4 units. So you might start at 4, maybe more. You might start off at like 5 and jump up to 10 or something like that, or higher, you know. You're looking for a pretty big rise in the pH. Depends on if you have monoprotic or diprotic. For diprotic, the second wave is a little less. For monoprotic, the second wave is bigger. But keep an eye on the pH because your trial titration could have had fairly large relative errors. And so your actual milliliters could be offset. And so you'll have to compensate for that on the fly. Is that clear? Okay. Uh-huh.
Just the like things like the unknown solvent of water.
Yeah, your trial titration, just get your unknown, go to the balance room over there, weigh out like 0.1 XXX grams, and then just run a titration, quick titration. You know, you don't have to set up all this pH meter stuff. You know, for your trial titration, it's just normal burette and Erlenmeyer and phenolphthalein. That's it. Just titrate it. So same titration as in Chem 4 and Chem 1A. If you overshoot, you can do as many trial titrations as you want, you know, until you feel comfortable with it. And then do the pH. But we have to keep in mind the time. You know, we don't have 1,000 minutes for data collection, so we've got to make the best use of the time that we have. All right, any other questions? Uh-huh.
Did you do anything else today besides this?
No, just this. Okay. All right, I'll stop talking. Go ahead and check out the equipment.